Welcome to Mathematical Analysis. We're working through Tom Apostol's legendary textbook, and today we're diving into Chapter 1, the real number system. Before we can prove anything, before we can do any real analysis, we need to answer one fundamental question. What exactly are the real numbers? And more importantly, how do we work with them rigorously? Let's find out. Apostol starts section 1.1 with a philosophical choice. There are two ways to introduce the real numbers, and the method you choose affects how you think about everything that follows. The first method is called the genetic approach. You start with the piano axioms for natural numbers. From there, you construct the integers by adding negatives. Then you construct the rationals by creating fractions. Finally, you fill in all the gaps between rationals using either Dedekind cuts or Cauchy sequences to arrive at the real numbers. This is beautiful, rigorous, and takes an entire course to do properly. Apostol acknowledges the genetic method on page 1, but he chooses a different path. He chooses the axiomatic method. As he states in section 1.1, we shall take the real numbers themselves as undefined objects satisfying certain axioms. What does this mean? It means we treat the real numbers as a black box. We don't care what they're made of. We don't care if they're cuts or sequences or mystical entities. We only care about how they behave. And their behavior is governed by exactly three groups of axioms. The field axioms give us algebra. The order axioms give us geometry and direction. And the completeness axiom, which we'll tackle later, is what separates the reals from the rationals. Together, these three groups completely characterize the real numbers. Let's examine each one. First, we establish the algebraic structure. We assume the existence of a set, capital R, equipped with two operations, addition and multiplication. Apostol lists axioms 1 through 5. These are the field axioms. Most of these should feel familiar from high school algebra, but now we're making them explicit and rigorous. Axiom 1 is commutativity. Addition and multiplication are commutative. 3 plus 5 equals 5 plus 3. 2 times 7 equals 7 times 2. Order doesn't matter. Axiom 2 is associativity. When adding or multiplying three numbers, it doesn't matter how you group them. 2 plus 3 plus 4 gives the same answer whether you compute 2 plus 3 first or 3 plus 4 first. Axiom 3 is the distributive law. Multiplication distributes over addition. 3 times the quantity 2 plus 5 equals 3 times 2 plus 3 times 5. This axiom is special because it's the bridge that connects our two operations. Without it, addition and multiplication would live in separate worlds. Axiom 4 guarantees the existence of identity elements. There exists a special number called 0, such that adding 0 to anything leaves it unchanged. And there exists a special number called 1, such that multiplying anything by 1 leaves it unchanged. Axiom 5 guarantees the existence of inverses. For every number x, there exists a negative, minus x, such that x plus minus x equals 0. And for every non-zero number x, there exists a reciprocal, 1 over x, such that x times 1 over x equals 1. But notice something crucial. Axiom 5 explicitly requires that 1 is not equal to 0. Why does this matter? If 1 equaled 0, our entire field would collapse. Every number would equal 0. We'd be working in what's called the trivial ring, which is mathematically valid but completely useless for analysis. Apostol ensures our universe is non-trivial. This seemingly small detail is mathematically profound. From these 5 axioms alone, we can derive all of valid algebra: cancellation laws, rules of signs, solutions to linear equations. Everything follows logically from these 5 simple rules. This is the power of the axiomatic approach. We don't memorize formulas, we prove them. If we stopped at the field axioms, we'd have a problem. The complex numbers also satisfy all 5 field axioms. So do the rational numbers. We need something more to capture what makes the reals special. We need a notion of size and direction. We need order. This brings us to section 1.3, the order axioms. We assume the existence of a relation, denoted by the less than symbol. This relation must satisfy 4 specific axioms that govern how numbers can be compared. Axiom 6 is called trichotomy, and it's the most powerful tool in our arsenal. It states that for any two real numbers, x and y, exactly one of 3 relations must hold. Either x equals y, or x is less than y, or x is greater than y. Exactly 1, not 2, not 0. This prevents all ambiguity and imposes what mathematicians call a total ordering on the set. Axiom 7 is transitivity. If x is less than y, and y is less than z, then x must be less than z. Order is consistent across multiple comparisons. This is what allows us to chain inequalities together. Axioms 8 and 9 ensure that our ordering plays nicely with our field operations. Axiom 8 says if x is less than y, then adding the same number to both sides preserves the inequality. Axiom 9 says multiplying both sides by a positive number preserves the inequality. These are the rules that make inequality manipulation work. Here's a profound insight. These order axioms rule out the complex numbers. Why? Suppose we try to order the complex numbers. If I were greater than 0, then by axiom 9, I times I would be greater than 0. But I squared equals -1, so -1 would be greater than 0. But we also know +1 is greater than 0, which means 0 is greater than -1. We've created a contradiction. -1 is greater than 0, and 0 is greater than -1. This violates axiom 6. The complex numbers cannot be ordered. Order is unique to the reals. Now we move from axioms to our first rigorous theorem. Theorem 1.1 introduces the quintessential proof technique of real analysis, the Epsilon argument. This single technique will appear in virtually every proof in this course, so understanding it deeply is absolutely critical. Let's deconstruct the logic. The hypothesis uses a universal quantifier. The inequality A is less than or equal to B plus epsilon holds for every positive epsilon. Every single one, no matter how small. The conclusion removes epsilon entirely and simply states that A is less than or equal to B. We're squeezing out the wiggle room. We'll prove this by contradiction. We assume the opposite of our conclusion. We assume A is strictly greater than B. Then we'll show this assumption leads to a logical impossibility, forcing us to reject it. Assume, for contradiction, that A is strictly greater than B. Then A minus B is strictly positive. There's a positive gap between these two numbers. Our strategy is to find a specific epsilon that fits inside this gap, creating a contradiction with our hypothesis. We need to choose a specific epsilon. Apostol chooses epsilon equals A minus B divided by 2. This is exactly half the gap between A and B. Is this a valid epsilon? Yes, absolutely. If A is greater than B, then A minus B is positive, so half of A minus B is also positive. This satisfies our requirement. Now we test whether our hypothesis holds for this specific epsilon. Our hypothesis claims that A is less than or equal to B plus epsilon for all epsilon. Let's check if it holds for our chosen epsilon. We need to compute B plus epsilon, which is B plus A minus B, all divided by 2. Let's simplify this carefully. We get a common denominator, 2b over 2 plus A minus B over 2. Combining the fractions gives us 2b plus A minus B all over 2. The 2b minus b simplifies to just b, leaving us with a plus b over 2. This is the arithmetic mean, the exact midpoint between a and b. Here's the key insight. Since a is strictly greater than b, their midpoint must be strictly less than a. Why? Because the midpoint is always between the two numbers. It's exactly halfway. So we have a plus b over 2 is strictly less than a. In other words, B plus epsilon is strictly less than A. But look at what we've discovered. Our hypothesis claimed that A is less than or equal to B plus epsilon for all epsilon greater than 0. But we've just found a specific epsilon for which A is strictly greater than B plus epsilon. We found a witness that violates the universal claim. This is a direct contradiction. The assumption that A is greater than B has led us to a logical impossibility. Therefore, this assumption must be false. By axiom 6, trichotomy, exactly one of 3 relations must hold. We've just proven that A greater than B is false. Therefore, A must be less than or equal to B. And that completes the proof. QED. Let's step back and understand the technique. We chose epsilon equals A minus B over 2, but we could have chosen A minus B over 3, or over 100, or over 1,000,000. Any positive number smaller than the gap would work. The specific choice is arbitrary. What matters is that we found a witness. This epsilon technique is the heartbeat of real analysis. You'll see it in limits, continuity, integration, and convergence. Master this argument and you've mastered the foundation of analysis. After establishing the abstract axioms, Apostol grounds them in geometry in section 1.4. He identifies the real numbers with points on a line. Each real number corresponds to exactly one point, and each point corresponds to exactly one real number. This is a bijection, a perfect one-to-one correspondence. This geometric picture is what makes real analysis visual and intuitive. On the number line, order becomes left and right. Numbers to the left are smaller. Addition becomes movement. Adding 3 means moving 3 units to the right. And the distance between two numbers becomes the absolute value of their difference. The abstract algebra has become concrete geometry. This geometric picture leads naturally to the concept of intervals in section 1.5. An interval is a set of real numbers between two endpoints. Apostol is rigorous with his notation here, using proper set builder notation. An open interval, denoted with parentheses, excludes both endpoints. The open interval from A to B is a set of all x such that A is strictly less than x and x is strictly less than b. We show this on the number line with hollow circles at the endpoints. For example, the open interval from 2 to 5 includes all numbers between 2 and 5, but not 2 itself and not 5 itself. A closed interval, denoted with square brackets, includes both endpoints. The closed interval from A to B is a set of all x such that A is less than or equal to x and x is less than or equal to b. We show this with solid circles at the endpoints. The closed interval from 2 to 5 includes 2, 5, and everything in between. We can also have half-open intervals, where one endpoint is included and one is excluded. And we have infinite intervals that extend forever in one direction. These use the infinity symbol, which is not a real number but represents unbounded growth in one direction. The crucial point is that intervals are sets. When we do analysis, we're performing operations on these sets. Is a point in an interval? Is one interval contained in another? What's the union or intersection of intervals? This set-theoretic language is essential to everything that follows. Let's recap what we've established. The field axioms give us the algebra of the real numbers. The order axioms give us the geometry and the number line. We've proven our first theorem using the Epsilon technique that will dominate this entire course. And we've learned the language of intervals and sets. But we're still missing something crucial. What's the difference between the rational numbers and the real numbers? Both satisfy the field axioms. Both satisfy the order axioms. The difference is completeness. The reals have no gaps. Every hole in the rationals has been filled. This is axiom 10, the completeness axiom, and it's the most difficult and most beautiful concept in chapter 1. We'll tackle it in the next video. If you found this helpful, please like and subscribe, and let me know in the comments which topic you'd like me to cover next. Thanks for watching.